Hi and welcome to this segment where we are going to look at the secant method. Recall in the previous video we looked at the Newton-Raphson method, where to find the next approximation to the root at xn plus 1 we computed it using the formula fxn minus f of xn divided by the derivative of f at xn. Now the secant method says that we will avoid computing the derivative of the function, and well, this comes in handy for some functions which are complicated, which we cannot solve, or which we cannot get an expression for its derivative. Okay, so some of these functions exist in real life and they are quite complicated to compute the derivatives. So we shall avoid that by getting an approximation to the derivative using something very simple from our calculus. Okay, our calculus. So if I can have just a simple illustration, here. Okay, so let's say we have a curve here, f of x, and then we want to find the derivative of our function f at the point xn. Let us assume this is our point xn. So we know that we can pick another point here, xn minus 1, and assume that these 2 points are so close. If the distance between them is delta x, we assume that the distance between them is really small, and then we can compute the derivative of f at xn by approximating it using if this is xn, we know that this is f of xn, and then this is xn minus 1, so we know that this point is f of xn minus 1. Okay, by using the normal formula for finding the gradient or the slope of a line, which is going to be given by the change in the vertical, which is f of xn minus this one here, f of xn minus 1 divided by the change in the horizontal here, which is xn minus 1. Of course, you remember this from your calculus, that we know that the limit as delta x approaches 0 of f dash at xn is given by whatever we have wrote here on the right hand side. Okay, sorry, no, it's that the f dash at xn is going to be given by the limit as delta x approaches 0 of whatever we have on the right hand side, where xn minus 1 equals to delta x. Okay, so we are just replacing our derivative with this computation here. So all we need to do now is just to substitute in back, so we can write it here neatly. We have xn plus 1 equals to xn minus f of xn over f dash of xn, where f dash of xn, we are approximating it with f of xn, so let us write short form f of xn, the value of f at xn, just to write it as fn, and then the value of f at xn minus 1, let us write it fn minus 1 divided by xn minus 1. Okay, so we will substitute this into that, so that we now have xn plus 1 equal to xn minus, I think now xn minus 1 over fn minus fn minus 1, then times f of xn. Okay, so we are going to simplify that further and then write xn plus 1. This is fn minus fn minus 1. So this is xn fn minus xn fn minus 1 minus xn f of xn. We said we are using fn, and then the negative and the negative here will have a positive, and then we have xn minus 1 times fn. Well, I hope I haven't made any error. I'm usually fond of making so many errors here. So this, that, and then this, that, xn fn, and then this, that, xn minus 1. Okay, assuming we have no errors, so some terms here cancel out. This term cancels out with that term, and then we can rearrange them and have xn minus 1 fn minus xn fn minus 1 all over fn minus fn minus 1, and this is xn plus 1. So this is the expression we are going to use to find the next approximation to the root, i.e. xn plus 1. So we see that we have eliminated the use of, the need to compute the derivative. We simply need the function values. Only that here you notice that on the right hand side we need to approximate, two starting values for our roots, two initial guesses. We need xn and we need xn minus 1, right? Yes, that's all we need, and then the rest is just to compute. So let us look at an example here. The example we have is that we want to find the real root of the function x cubed minus 2x minus 5 equals to 0, okay, using the secant method. So they say let the two initial approximations be given by x, write minus 1, x negative 1 is 2, and they say that x naught is 3. So we have all we need. We know that our f of x is here, okay. So here we see that at n is equals to 0, okay, we can say at n is equals to 0, let us substitute in here, and then we see at n is equals to 0 we have x1, okay, equals to 0 minus 1, that is x minus 1, then n is 0, that is f0 minus x naught f minus 1 divided by f0 minus f minus 1. We are just substituting in for the value of n as 0 here, and we have everything. What is xn? X negative 1 we are being given, it has been given to us as that. And then what do we have for x naught? We also have x naught as that. How do we compute f0? F0 is simply f of x naught, okay, which is equals to f of 3, which is equals to 3 cubed minus 2 times 3 minus 5, okay. And then f negative 1, what is f negative 1? This is simply f at x negative 1, which is simply f, what is x negative 1? 2, f of 2. Then we just substitute this value in here, which is 2 to the power 3 minus 2 times 3 minus 5. Alright, okay, so that's all we'll need. And then perhaps just for the sake of orderliness here, maybe you can have a table. We shall need xn, what else shall we need? We shall need xn minus 1. Then what else do we need? we need n, we need xn minus 1, then we need fn minus 1, then we need fn, and then we need the root, and then perhaps we need to compute the error. Okay, so we need the okay, so we need n. What else do we need? Xn minus 1, then we need xn. What else do we need? We need f n minus 1, and then we need f n. That is remember this one here we said is f at xn minus 1, and then we said this one here is f at xn. Okay, and then we need the root xn plus 1. And how do we find xn plus 1? The formula is just above us there. It is x minus 1 times, oh no, in the general formula, since here we have n, so it is x here. It is xn minus 1 times fn minus xn times fn minus 1 divide by fn minus fn minus 1. And then how do we compute the error? Xn minus 1 minus xn, the absolute value. Then the rest is for us to fill in. When n is 0, the value here they gave to us is 2, and then x0 is 3. We compute fn minus 1. Do I have the value? Yes, I hope it is correct. Fn minus 1 is negative 1, i.e. f of 2, yeah, I think it is. This is 8 minus 4 is 4 minus 5 is negative 1. And then confirm that f of 3, that is f of n, when you substitute in this one, that it is 16. And then you compute the root by, you have everything. You have this, you have that, you have that, and then you have that. Just substitute them in here and then find the value you get. And then here, of course, since it's the first, there's no need to find we don't have the error here. Okay, we can't compute the error because it is xn minus 1 minus, oh, we can compute the error. We have xn minus 1 minus xn. What is that? This is xn minus 1. Oh, okay, the error is xn minus xn minus 1, the previous value, minus xn minus 1. So we have here xn is 2 minus 1, I mean 3 minus 1, sorry, 3 minus 2, which is 1. Okay, and then this one here you compute. I found it is 2.05 NF. It's not that I found, it's even in the notes. You'll find it in the notes, 2 something and so on. So when n is now 1, this is going to be 1 minus 1, which is x naught. Okay, but we know already x naught. What is x naught? X naught is 3, so this value comes here. This is 3. And then when n is 1, this is x1. Okay, but we know already x1. x1 is the value we got here. At the step n is equals to 0, this is x1. Okay, so you just carry the value here and then you put it here, 2.058 something, and then start computing this. This is f of 3, and then this is f of xn, which we said is 2.058 blah blah blah, and then you compute the next approximation, then you find the error, then you come here, and so on and so on and so on. Okay, so as usual, I leave this hard part for you to fill in. Try to fill it in, not that try, please fill it in, because you have to do this like to get the feeling. Maybe you may be asked just to compute 2 or 3, to fill in the values, fill in the figures, or 4 lines and so on. Of course, determination criteria, either after a finite number of steps or after a given level of tolerance has been used. So for this one here, I would like to complete this video here by taking you to the simple algorithm which can be used for this. A reminder, these algorithms I'm writing, they are written in Python, but we are going to use MATLAB, and therefore just follow the idea here. The idea is the same. You can probably even write better algorithms, and this is just for educational purposes, so it is written very quickly. So very quickly, the video is being quite long, so we define these ones here. This is just the syntax, the way maybe a function is written. The way function is written here is very different from the way it is written in Python. It's different from the way it is written in C++ and so on. So don't mind about this. These ones here, you just need to look up maybe here how do you write a function, and then you write. Even in MATLAB, you can say that how do you write a function, and then you write it. So in here we define the function, and then we return these values here. Okay, this is the function which we already had, which we are returning. And then we start our initial roots, which we had x0 and x1. Okay, and then we compute f of 0 to be what was it? F of 0. Okay, we compute f of 0 to be f at x0. This one here, this initial root. This was what we call our x minus 1. Okay, and then f1 is the one which was called the x0 when x1 is equals to 3. I wrote this because it's just logical. I didn't know any other way of writing that x minus 1 or x0 and so on. No, x0 is right, but x minus 1 is not that easy. I didn't know how to illustrate it here, so we just said, okay, let this, the x0, be the other one, x minus 1, and then let the x1 be the x0 in the notes. Okay, so here this, you've already seen this. So what is f of 0? It's just the value of the function here, f at this point here. And then what is f1? The value of the function at 3. Why did I write this? I was just writing this just to see that the correct values, or the input, I was just testing it to see that I have the correct input. So here I have I set an error, I set a tolerance, I set a count. You've seen this countless times, and then you've also seen this while loop. So you see that the things are more or less the same. We see the while loop, so we are going to run this loop while the error is greater than the tolerance. So what we have here, we have x2. Okay, now this is where you have to follow x2, that is xn plus 1 equals to, then we just follow the formula which we have, x0 f1. Maybe we can just write this one here, x2, and then you say, oh, okay, write x2, that is when n is equals to 1. Then you will see that you have exactly this this expression. Okay, then we compute the error, we count. Okay, we update our count after this has run. Okay, and then this you've seen countless time. We are just printing out the count. I print out the x0 to see the value we have. I print out the f of x0, x1, and then f of x1, and then I print out the root, which is x2, because we are computing for x2, which is the root. And then I also compute out the error, print out the error just to see. So the update here is the most important. Okay, the update here is the most important. Please note that x0, okay, now becomes x1, and then x1 now takes on the value of x2. Let's see here in the notes here. So here in the update, after we have computed x1, okay, now our x minus 1 will become x0. Okay, you just go one step ahead, and then our x0 now becomes x1, because now to compute x2 you will need x1 and x0. Is that okay? Yes. So you just step the one, you just take a step up. Okay, I don't know if that really makes sense, but if you take a minute or two just to see, you can just try to convince yourself that this update is correct. X node now becomes X1, so this will be in the, so when I'm finding X3, the next one, which is X3, but still this is just X2, so X3 we shall have here X1, okay, and then we shall have here X2, and then this will be F2, and then this will be F1, okay, in your mind, in your head, but of course in writing here it does not change. So just get the logic of the update here and everything else will be okay. So I don't want to talk any much more. I feel I have really talked a lot. Sometimes if you talk a lot you lose the people. So if we run that, we will compare with what we have in the notes here. We have the iteration count, we have X naught is 2, f of X naught is -1, we have already seen that, X1 is 3, and then f of X1 is 16, and then we find the root. This is the root also as it appears in the notes, okay? You can check that with hand. I mean, you can check that in the notes, and you can also compute it by hand. So we check that in the next iteration, we also had that, and then the X naught, then the X naught for the second one here, which was updated, and then f of X naught, and then go on and on, okay? So check that everything here is the same with what is computed, okay? So yeah, maybe if this is not that neat, you can always go in the program here and just change, okay, and then just change. Maybe if you want to remove some of these things, maybe do we need a count? Okay, let's see, we need X naught. No, let us just display maybe the iteration number and then the root and the error. Perhaps that will be enough if that's okay. So I save that, and then go here, clear that, and then we try to run it again. Yes, so we have the iteration count and then the root and then the error. Have the iteration count, the root, and then the error. So I beg to stop there, and thank you very much, and see you in the next lecture.